Okay, so picking up where we left off last time, so we were talking about the chain rule, and remember the fundamental point of view I want you to have about the chain rule is that it concerns compositions of multivariable functions. So the point of view should be on the multivariable functions, not on the variables that we use to represent the multivariable functions, right? So looking back real quick at it, here it is. Yeah, right? So two functions, their derivative matrices, and the derivative matrix of their compositions, right? So this is all in terms of functions and matrices. Okay, now that said, sometimes this is more than you need. It's bulkier and more powerful than sometimes you just want to know just one little partial derivative. And in such a case, this other point of view can be very convenient. And this actually comes up quite a bit. So here is a pair of multivariable functions. Notice that what comes out of f is what goes in to g. Right? So if we talk about the composition, then okay, well, we can write down exactly what the chain rule says. Notice that the derivative of f is here. The derivative of g is here. F is first, g is second. Remember, and of course remember what that means about which is on the left and which is on the right in which notation. And you just got to keep that straight. And then the composition that takes the x's all the way to the z's, its derivative matrix is like that, and made up of the partials of the z's with respect to the x's. Okay, now with this setup having been made, and all this is the matrix form of the chain rule, notice that one element of the derivative matrix is an element in a matrix product, and we know how to multiply matrices. You take the corresponding row of the left matrix and the corresponding column of the right matrix. And so we're just going to literally just dot, that, dot, that, and you can see that dot product in action by the corresponding elements being multiplied, and then those products being added per our usual dot product formula. Okay, so nice little punchline then. If you need to know the entire derivative matrix, then yeah, sure, you use the big gun of the matrix form of the chain rule. But if you just need to know one individual partial of the composition, this relatively compact formula, very handy for that purpose. Notice there's no sort of unnecessary stuff in here. I didn't use these elements here or there or here or there at all. Right? So why bother writing down these entire matrices if you only need just this little bit? Okay, so has its moments. Now, before we go on and see some of the nice applications of this and different ways to think about it, etc., I do want to warn you about a notational problem. So this is a very common mistake. I see this on exam papers all the time, and it's very tempting. And I understand why students would get this wrong, but it's very important not to get it wrong. So again, here's our new formula. And a lot of students look at just this part right here and say, hey, I don't really feel like I need the rest of this. After all, those appear to cancel, thus leaving me only with partial zi in the numerator and partial xj in the denominator. Isn't this good as it is? So again, you can see the temptation, right? And this is absolutely wrong, 100% wrong. Right? Now, we know it's wrong because, after all, we just got through discussing how this is what you get when you dot the entire row with the entire that's how matrix multiplication works. There is nothing to argue about. This is the right answer. So why does this illusion that you can just cancel these partial y's, why doesn't that argument work, and what's going on here? Right. So ultimately the point is this. that these things here are not the same thing. They're just not. These are, they both represent how much y1 is changing in some sense, in some context, but the contexts are different. Right? So, in particular, if we look at the one on the left here, this partial y1 on the left, that's part of this partial derivative. How does a partial derivative work that I have circled here? Well, I have to hold all the other input variables constant. So I would have to hold all of the other y variables constant in order to talk about the y1 partial of zi. So here, what I have written as if it's a thing, as if it means something by itself, partial y1, right? This does represent how much y1 changes, but again, in a context where the other y's have to be constant. Now, by contrast, let's think about what this, I'm going to use a different color here, this partial y1. What does that mean? Well, that's part of an entirely different story, completely different story. In this other story, I'm taking a partial of y1 with respect to xj, which means the other x variables are constant. But it remains that xj is changing, and if you change xj, all the y's are going to be changing. All the y variables depend on xj. You change xj, all those y variables are going to be changing. Right? So in this story, these other y variables are not constant. So you cannot do algebra between these two things because they are describing totally different scenarios. Those two things, the partial y1s, just aren't the same. Does that make sense? It's like if you have two, that's a silly metaphor, but if you have two totally different movies in which there's a character named Bob, they're not the same person. Right? Same thing here. Two totally different scenarios in which, in their different contexts, it makes sense to talk about how much y1 is changing, but it remains they're different scenarios. Okay, so please don't make that mistake. Very common landmine to step on. And of course, if you miss all of these terms, then you're going to get, not only are you going to get a really, really wrong answer, but of course your reasoning is itself going to be really, really wrong. And remember, it's all about the reasoning. Okay, all right. Moving along. So, I want to give you a way of thinking about this equation. Now, this is just a recopy of the equation that we were just looking at. So that you don't have to write down the great big matrix equation every single time in order to draw your corresponding conclusion about what this equation should be. And here's my point of view, and keep in mind our setup was that the y's are functions of the x's, and the z's are functions of the y's. So here's our little diagram representing the variables. And let's remind ourselves here that we're thinking about how much does zi change as xj changes. Right? Okay. Well, wait. So further, because this is a partial with respect to xj, all of these other x variables are to be understood to be constant for the purposes of this calculation. Those xj's are not, x sub not j are not allowed to change. Okay? So what happens in this scenario? And I propose, and this is just why I like to think about it. There's different points of view, I'm sure. I propose that when you change xj, that's going to cause a kind of a cascade of different changes that we can just keep track of. So in particular, when you change xj, that will cause y1 to change. And as y1 changes, that will cause zi to change. And that's where this term comes from. Right? You change xj, this partial derivative here tells you how much more than that y1 will change, and then this factor here tells you how much more than that will be contributed to how much zi is changing. But that's, of course, not the only thing that's going to happen. When you change xj, you will also change y2, and that will make its own independent contribution to how much zi will change. And that gives you the next term that I don't have written down there, but you can imagine there's the next term that's what you might call the y2 term. And then et cetera, and then lastly, as xj changes, that will cause ym to change, and that ym changing will contribute to how much zi changes, and there's that term. Okay, how's everybody doing so far? That's just a point of view now. What I like about this point of view is, again, I don't have to write down the matrix in order to be able to motivate the formula. I can just think to myself, well, look, there's only so many of these, what we call intermediate variables, the variables in the middle, as it were. Each one of these intermediate variables corresponds to a path along which changes can propagate. And each path corresponds then to a term in the summation that keeps track of the partial derivative that we're interested in. So intermediate variables give rise to paths, which give rise to terms. And thus, if you just know what your intermediate variables are, right? So here's all my intermediate variables. You're going to get a term corresponding to each one of those intermediate variables. And notice, it's always partial zi in the left numerator, and it's always partial xj in the right denominator. That part's the same. It's just what intermediate variable, which y, is in the other two positions seemingly canceling, which of course it's not, right? But in those positions, it's easy to remember where they go because they go where they look like they cancel. So, like I say, different point of view, and very convenient in some cases. So let's see one. Moving down, here is the question we're going to address. Notice I'm given a couple of functions, f and g, and I've got some explicit formulas. So f takes in the x variables and spits out the y variables. I'm going to draw my diagram over here accordingly. This f gives rise to that part of the diagram. Notice that g takes in the y's and then spits out the z's, and that gives rise to what you might call that part of the diagram. All right, so I find this extremely useful, by the way, almost indispensable if you're going to take this point of view on the change. You're going to bypass matrices, right? For convenience, then that's really essential to have this diagram. I thought I felt the sneeze coming on. Sorry. Okay, so how are we doing so far? Got a diagram. Now we have to make use of it. The question that is before us is to compute the partial of z2. Okay, well there it is. With respect to x2. Okay, there that is. So the composition partial that I want. Here's the input variable, here's the output variable. Where are my intermediate variables? Well, my intermediate variables are y1 and y2. Or, said differently, there is a what you might call a y1 path that gives rise to this y1 term. And there is this y2 path that gives rise to what you might call this y2 term. Notice the partial z2's are exactly where they're supposed to be. The partial x2's are where they're supposed to be. And there's your chain rule. Right? I find this very mechanical, right? This is very sort of, take your equations, make your diagram, view your paths, and write down your corresponding terms. Totally mechanical. Okay. Now, then there's various things to be computed. So let's just look real quick at this one. Partial of z2 with respect to y1. Don't forget, z2, there it is. We have an explicit formula for it. z2 is y1 cubed. Right, so taking the partial with respect to y1, you take the y1 partial of that, and of course that's an easy one, and it gives you 3y1 squared. Okay. Everybody happy? Okay. All right. Okay. So we're moving along. There is a mistake that gets made very often. I call it confusion of variables. It's a pretty standard notion. The idea is represented, I think, very nicely in this Calc 1 question, and I know y'all know Calc 1, and y'all are going to spot the mistake immediately, I'm sure. But here's a couple of functions, nothing wrong with them, perfectly good, two functions, f and g. Perfectly reasonable question. Hey, what's the derivative of the composition? Nothing wrong, no problem, right? Reasonable question to ask. And then here's the ever so slightly too fast and careless solution where the student first writes down that the derivative of the composition is the product of the individual derivatives. The individual derivatives they compute like so. They multiply to get 6x cubed, which of course is wrong. Right? So now, what did the student do wrong here? What the student did wrong here is, again, this was a little too careless. It is kind of f prime times g prime. Okay, sure. But critically, the g prime has to be evaluated at f of x. Namely at x squared, not at x. That's a point of view anyway. This is what they showed me in high school, right? The point is it's g prime of f of x instead of g prime of x. And I got to tell you, this weirded me out for a long time. But it says right here, g is a function of x. Why am I plugging in f of x? It just seems arbitrary, and I don't know. I found this very uncomfortable. So I think the problem is that we have inadvertently committed a confusion of variables. Here's how I think things should be set up. I have a couple of functions, f and g, and I'll point out the following. Now, let's talk about what are we going to call the variable that comes out of the function f. I need to give this variable a name. Can I call this x? No. Nonsense. X is what goes in to the function f. You can't give the same name to the input variable and the output variable. That's outrageous. Right? So I can't call it x, so let's call it y. Okay, fine, but now recall, though, the thing that comes out of f is supposed to be the thing that goes in to g. That means that I really ought to call g a function of y, not a function of x. So really, I should have, first cat out of the bag, I should have said, you know what, I can't do that. I can't think of g as a function of x anymore. I want to compose them. X is the input to f. It can't be the input to g. I need to rewrite g like so. So this formula I had started with should be rewritten as this. Now, a lot of people get uncomfortable with, hey, whoa, can you just do that? Yeah, absolutely. G is a function. X is a dummy variable. It's a placeholder. I could call it Bob if I want to. It doesn't matter what you call it, right? G, the function itself, is the act of cubing whatever you give me. That's what G is. And I can represent the act of cubing whatever you give me by using any dummy variable. And again, as discussed up here, to make our diagram make sense, I think it ought to be called y, and it should not be called x. Does that make sense to everybody? All right. Oh, yeah. Mm-hmm.
I have a question about like g prime of f of x.
Yeah.
Like the computation from that to like 3x squared or whatever.
Yeah.
I thought it's going to be like if you substitute like x to x squared, like to gx, that would be like x squared to the third.
So g prime is 3 times the square of whatever the input is, right? But the input is supposed to be f of x, which is x squared.
So you can't like substitute in like x squared for like x in g of x.
Yeah, but see what I'm going to do is I'm going to avoid your question instead of clarifying, because what you're doing is illustrating my point, which is it is confusing. Right? And what I've given you is an alternative that allows you to avoid that unnecessary problem in the first place. Right? And I think that's really the better way to go. Right? So the far better. So let me show you how it works out doing it what I think is the much better way. So with the function rewritten, avoiding the confusion of variables, now it's perfectly clear what is x, what is y, what is z. Notice I don't even have to be careful. I can just write down again. Fast and sloppy. Derivative of compositions, the product of the derivatives. I don't have to worry about what's evaluated where. G prime, right, is 3y squared. F prime is 2x. This multiplies to 6y squared x, which, again, I didn't have to remember anything. I can just immediately see then that y, being the thing that goes into g, therefore being the thing that comes out of f, therefore is x squared. And you put that right in there, and we get the answer that we were looking for. So the notation keeps track for us. You see what I'm saying? And so this I mean, I don't know if this was your intention, but the confusion that was hassling you was the same confusion that was hassling me when I was in high school. It's all a consequence of bad choices of variable names, right? And don't try to make sense out of stuff that doesn't make sense. This is my general rule. Is that satisfying? Okay. Yeah. Okay. All right. Now this is I started in the context of single variable just to illustrate the fundamentally unnatural idea of confusion of variables. But now let's apply it in a multivariable context. It's morally the same idea. Here I have a couple of functions given. And now let's avoid the confusion of variables. F is given as a function of x and y. Okay, what are we going to call the outputs? I can't call them x and y. X and y are the inputs. So, okay, let's call these outputs u and v. And those being the outputs, that means that those are the inputs to the function g, and so I should rewrite g. Same function, don't change the function. But I'm going to rewrite that function g in terms of this much more natural choice of dummy variables. And having done that, everything else just falls into place. So the first function being f, here's the df that goes on the right, which is first. In the way you multiply matrices, again, be super careful, please, on which order you put the matrices. The first has to be first. Sometimes it's left on the diagram, but it's right in the matrix product. Please be very, very careful. I've been burned badly on this in the past myself, so please be careful. G being second, there's its derivative matrix. Going as it does second, it's the left matrix in the product. And again, it's just a matter of multiplying it out. And the notation has kept track for me of what to plug into where. Specifically, what am I going to do about this u right there? What do I plug in for u? Okay, well, u is the second output from f. And therefore, it is... I said second, I meant first. It's the first output from f, and therefore it's x squared plus y squared. Everybody happy? Use different dummy variables. Don't confuse your variables. This problem will never rear its ugly head and will never bother you. Okay. All right. Now, this is a special case of a larger problem. This larger problem is a little bit subtle. Let's suppose, you're given a bunch of equations. In fact, let me just go, I'll momentarily skip and then come back to above. Let's suppose you're given a bunch of variables related like so. So y1 is x1 plus x2, and et cetera, et cetera. And you draw what seems to be the corresponding diagram. It would look like this. And I claim we already have a major problem. So, for example, let's just try to make sense out of this expression, partial of z1 with respect to x1. What does that even mean? Okay, now I'm going to make an honest attempt to make sense out of what that means in the context of this diagram. Well, z1 is a function of these three variables. There's the formula for it right there. z1, you can see it is explicitly given as a function of x1, y1, and y2. Okay, a partial derivative with respect to x1 means that I let that be a variable and hold the other variables constant, but I can't vary x1 and require y1 and y2 to be constant, because y1 is a function of x1. Right? If I change x1, I will be changing y1. So I don't even know what this means as written. Everybody see why this is nasty? Right? Did we have what went wrong here? Right? So let me explain what I think went wrong, and that is that we overinterpreted from this idea of diagrams and intermediate variables and such. Remember, this idea of intermediate variables and diagrams and looking at paths is just an alternative interpretation of a matrix product. This matrix product came from the only chain rule that we've given any actual justification for, and that is this one, that a derivative of why am I in gray mode? That a derivative of a composition is a product, a matrix product of the individual derivatives. This chain rule, the only chain rule we've actually justified, only applies, only, strictly, exclusively, if you are composing multivariable functions, where what comes out of the first function is precisely exactly what goes in to the second function. So if you're going to apply the chain rule as we understand it, you have to, in fact, have things set up as literally a composition of multivariable functions. And that's just not the case in this this nonsense that I wrote down here. I can't break this up as a composition. Specifically, if it were going to be a composition, among other things, right? I need to be able to say, there's my first function, inputs and outputs, unambiguously identified. Here's my second function, inputs and outputs unambiguously identified. The inputs are independent of each other, right? Y1 is not a function of Y2. Y2 is not a function of Y1. X1 is not a function of X2. X2 is not a function of X1, right? So we have independent inputs, unambiguous names, and, as I've noted here, what comes out of the first function needs to be exactly what goes in to the second function. And this is what I claim just does not make any sense. This is not representing, as written, this is not representing a composition of functions. There is no chain rule to make sense out of it here. Does that make sense? So this whole business about a diagram, again, is a shorthand to represent compositions of functions and the resulting matrix product. We don't have a chain rule for generic, arbitrary, diagrams like this. We just don't. Okay, so the fix, no big deal. The fix is to introduce a new kind of semi-fictitious variable. I'm going to make up a variable to put right there that is a function of just x1. Let's see here. Okay, here we go. There it is. Right? x1 star. And you see the formula. x1 star is just x1. So I haven't actually done anything, right? Now, cosmetically, it looks like I've introduced a new variable here called x1. But it's really just x. X1 star. It's really just x1. But it allows me to rewrite now. I can, without any problems at all, I can say z1 is a function of x1 star, y1 and y2, like so. Right? Let's abandon this confusing formula right here that led to all the problems in the first place. Oh, that looks like I'm highlighting it. I'm sorry. Let me scratch. There we go. Let's abandon that old formula. That was the initial problem. And now I have no issues. The awkwardness has gone away. This weirdo, I don't even know what this is diagram is gone. And now I just have, very simply, a composition of functions. And you can see the composition right here in the structure. Here are the ins and outs of f. Here are the ins and outs of G. Notice that what comes out of F is what goes into G. I literally have a composition of functions. I totally have a chain rule that will allow me to address this composition. And so my little shortcut, little hack, kind of convenient point of view about intermediate variables and terms and all that. Yeah, cool. It's all good at this point. And specifically, looking at the partial of Z1 with respect to X1. Oh, gosh. With respect to X1, I get an X1 star term and a Y1 term and a y2 term. Just looking at my intermediate variables for my diagram, and now it's just a matter of, there's various partial derivatives that you'll need to compute from these equations, and you plug it in and you work it out, and it's just details. Everybody good? So heads up on this business, and again, it can be very confusing and unsatisfying to try to make sense out of stuff like this. Make sure that you reconceive it as needed to actually look like this, not that. Okay. All right. Let's move to the next thing. Okay, second derivatives. There's a couple of different ways that you can approach this. I've toyed with formalizing this rule, and it's just not worth it. It's way more complicated to write down a formal, theorem here than it is to just kind of get the gist of the classic first example that everyone sees their first time. So that's what I'm going to do. I'm just going to show you this classic first example. I'm going to explain what the process, how you avoid the confusion that naturally arises, right? Where that confusion is, how do you get rid of it, right? And then I think when you see that example worked out, you'll kind of see the pattern. So here we go. Let's see here. Oh, good. Okay, we got good time. So ultimately what the big trick is going to be is this right here. If you have z as a function of x and y, I make the modest observation that so are its partials. We've made this observation before, right, when we were talking about higher order partials. If z is some expression involving x's and y's, its partials should be expected to be represented by an expression involving x's and y's. Okay, we'll see where that comes up in a minute. Okay, diving in to our example. Again, classic first example. Suppose I have a nice, friendly C2, nice, convenient function of x and y. Z is a function of x and y. I indicate thusly in my diagram that I'm forming. Now, it says here r and theta are the usual polar coordinates. Let me remind you, there's different ways to think about polar coordinates. And the one I like to push is this idea that you should think of it as a function, that x and y are these explicit functions of r and theta. So x is r cosine theta, y is r sine theta, right? And so thought of as a function, I have this side then of my diagram. Okay, with all of that set up, notice the question is to compute a second partial, but specifically a second partial of z with respect to r. In other words, we want to take a second partial through a composition. How do you do that without actually just plugging the whole thing in and doing it brute force? Okay. So we're going to compute this second partial one at a time. We're going to start off with partial of z with respect to r. There's z, there's r. There's two paths. Oh, gosh. Two paths and thus two terms. That's just a single partial. Okay, nothing interesting's happened yet. Note a couple of quick simplifications, and again, not that interesting, but because x and y are the usual functions of r and theta, it's easy to take the partial of x with respect to r. Partial of r cosine theta with respect to r is just cosine theta. Likewise, over here. And then notice I also have, nothing sophisticated happening here. This is just kind of an alternative notation here. I'm just rewriting the partial of z with respect to y, let's say. I'm just rewriting this in a perfectly, equivalent alternative notation, writing it as zy. You'll see why that's useful in a minute. Okay, now, having computed the first partial, the second partial that we're interested in then is just going to be the r partial of that r partial that we just computed. And so that leaves us trying to make sense out, leaves us trying to make sense out of this expression right here. Lots to say about this expression right here. Is everybody with me down to here? All right. Okay. First, a lucky break. You won't always get this lucky. Sometimes you do. Take the wins when you can get them. The lucky break is to observe that if I consider this first term, noting that the partial is with respect to r, notice that means, because of what partial derivatives are, that means that theta is to be viewed as a constant. And if theta is a constant, then that means that cosine theta is also a constant, and constants will just pop right outside of the derivative. Is that cool? Everybody all right? Now, again, we got lucky that time. What would I have done if I hadn't been so lucky? What if, in addition to having, some non-constant thing, what if this was like a function of r, or had some r's in it, and therefore I couldn't treat it as a constant for the r partial? Well, then I just have a product, and I just write down the product rule. Right? So that's just an extra layer of annoyance that I don't want to get bogged down in this example, and that's why I chose this nice, easy one for this first time through. But anyway, you would just use the product rule. It's actually not that big a deal. Okay, all right, so that leaves us then with trying to make sense out of this first term, we really only need to make sense out of the partial of zx with respect to r. And here's where we're going to use the big point from up here. The big point being that if you have, in fact, a function of x and y, the partials are too. That's the big point. If z is a function of x and y, then zx is a function of x and y, and zy is a function of x and y, and I'm just going to indicate thusly on the diagram. So this thing here, this zx, it's a function of x and y, and let's represent that accordingly. And likewise, zy over here, that's a function of x and y, and so let's indicate correspondingly on the diagram. Everybody with me? So now it's really not that hard to see what's going on with this expression right here, partial of zx with respect to r. After all, zx is there, and r is there. And let's see here. I have two paths. There's the x path that gives me what you might call the x term. There's, I guess I'll use yellow. There's the y path that gives me this y term, you might call it. And this is just, missed. This is just the chain rule applied, thinking about those intermediate variables. What do you think? Everybody see what I've got in purple there? It's just a rewrite using the chain rule. I've got a blue path and a yellow path. Therefore, I've got a blue term and a yellow term. And, of course, the zx stays right where it should have been. And the r stays right where it should have been as well. Okay, analogously, now over here on the other side, looking at the next term over here, looking at partial of zy with respect to r. Okay, well, zy is there, r is there. Right, again, I have two paths. There's I missed. There's this x path that gives me this x term. And there is this, I guess you use red, I keep missing. I don't know why I'm doing that. This y path that gives me this y term. And, of course, constant sine theta, multiplicative constants come along for the ride as multiplicative constants do. Everybody okay? Everybody following me? So, again, notice the big trick here. The thing that makes this all make sense is this choice right here, that when you have partials of z showing up in your calculation, as they do, right? They show up with the very first partial that you take. Put them on the diagram, acknowledging what they are functions of. And everything else, just follow the diagram. Do exactly what the diagram tells you to do. Okay. All right. So it's all over but the shouting. There is just a little bit of an observation to make here. Z came to us as a function of x and y. This says take its x partial and then take the x partial of that. That's a thing. That's the second partial with respect to x. That's the definition of zxx. That you can just write down. There's no chain rule inside of here because there's not multiple functions in between z and x. Z is immediately a function of x. So no chain rule at all there. That's just a rewrite. Likewise, this is just a rewrite, and this and this. And then a little bit more trig, polar coordinates, easy partials. This is just taking the appropriate partials of the appropriate polar coordinates. Constants, of course. Don't lose track of those. And then you can kind of multiply things out and collect terms. And the final punchline is this right here. How we doing? Okay. So that's the big idea. There are different manifestations of this big idea, but if you just follow this as a pattern, it'll all work out. Now let me try to persuade you why this is useful and why it's interesting. And I'm going to recognize, by the way, that this is actually not in the textbook. The textbook doesn't, I didn't see it anyway, but I don't think the textbook addressed the matter of second derivatives through the chain rule, through a composition. And to be fair, there's a lot of different topics that could be interesting. But I found in my physics, which is not that different from engineering experience, that this came up massively. It was a huge deal, and it was absolutely essential that I actually understand this. So that's why I've put this second derivative with the chain rule on the content syllabus. And you'll notice if you look at the content syllabus, it's in the included material column, right? So this, even though it's not part of the book, it is part of the course. It is something you're responsible for, so that's why I added it in there. So why, though? What's this good for? And here's my example. It's going to take me a minute to build up to it, but I want to point out this thing called the Laplacian operator. You may have seen this previously. It is massively important in physics. If you want to understand how waves move or how heat transfers or how electrons behave in a electric potential system, right? The Laplacian is a major player in all of those discussions. It's a really big deal. Okay, so that said, sometimes it's easier to understand the Laplacian if you write it in spherical coordinates. Now you may be thinking, this doesn't look like it helped. This looks worse. This looks nastier, right? If I had my choice between these, if I didn't know what I know, right? If I just naively going to pick which one do you want to deal with, wouldn't you naturally probably want to pick the rectangular one? Because it's shorter, smaller, less Greek letters, less trig, less ink overall. It just seems to have all the advantages, right? Okay. Now, real quick, where did this come from? How is it that these two things are the same? This is something that you can do for yourselves. I'm not recommending that you should. This one is, I'm going to say, too tedious, and I don't think it's worth your time. Right? If you just really want to, if you're looking for a challenge, okay, go ahead. But I don't really recommend this. What you can do is realize that if, just like on the previous page, if you have a function of rectangular variables, and if you want to think in terms of spherical coordinates, and keep in mind spherical coordinates means x, y, z are functions of rho, phi, theta, right? Then you can address questions like, what is the second partial of f with respect to theta by using methods just like on the previous page. This is a second derivative that's going through a composition. Just use all the same ideas on the previous page. Okay, it's spherical instead of polar. A little bit of uglier with the algebra. But all the same basic ideas, and you can rewrite this in rectangular coordinates. You can do the same for everything else in this expression. And if you compute all of these different partials, yikes, it will simplify to that Laplacian. Okay, so thankfully, someone else did this for us, and you don't therefore have to do it. We can just take advantage of it. Okay, now again, doesn't look like it's a win. You give me my choice naively between these, I got to say I'm leaning toward this one as looking simpler. Now let me try to persuade you that that's a mistake. Right? The rectangular Laplacian is very often not the one you want to deal with. Here is my example. Let's think about electric potential voltage. You have a charge, right? Charge creates an electric field. Electric field creates what's called electric potential, right? Okay. Turns out that is described by this equation, in which you will notice the Laplacian figures very prominently. All right? You might want to test a candidate solution. I want to test this one. By the way, side note, the reason I want to test this as a possible candidate is because this is the right answer. It's one of the right answers. It's kind of the elemental default, kind of the primary correct answer. So this is something to which I want to apply the Laplacian, and I hope that it will turn out to be 0. Again, it will, but I've got to actually do that, right? So, okay, so here's your options. You can apply the Laplacian in either rectangular form or spherical form to your candidate function, which you can write in either rectangular form or spherical form, and you can crank out either this or this to see if you get 0. Now, so which would you rather? Would you rather compute this expression or would you rather compute this expression? Now, again, it's not looking, I don't think I've made a sale yet, right? Because this is looking not that bad, and this is looking way worse. But let me walk you through how this is going to play out. If you look at this expression right here, you're gonna, you can almost kind of see it coming. I'm going to start with taking a z partial of this expression. There's a fraction, there's a radical, there's a function of z under the radical, there's a bunch of factors, and it gets a little annoying even with the first partial. Then you got to take the z partial of that, and it gets really inconvenient. It's doable. It'll take you a page or two, right, to crank out this expression. And you can do it, but it's not pretty. Now let's look at this expression. I'm going to do this in seconds without writing anything down. This is a super easy calculation. Check it out. We start with a theta partial of a function that doesn't have any thetas in it. That's 0. Poof. Right? It's pretty awesome. This entire term here, the very first thing that happens is it disappears in a puff of smoke, and that's just gone. Right? So that goes away. Likewise, looking at this applied to that. Very first step, phi partial. There's no phis in there. Poof. It disappears. Right? So all of this is gone. And then let's look at this next. The next one we're going to have to actually do a little bit of work, not a lot, but one of the factors, when you take the rho partial of k over rho, you're going to have rho squared in the denominator, right? And rho squared in the denominator times this rho squared in the numerator makes this a constant. And of course, whatever partial you take of a constant, 0. And so that disappears too. And so it's all gone. We got a 0, we win. We've confirmed that this is a solution to Laplace's equation. And it was way, 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 way easier than this nightmare right here. If you don't believe me, give it a try. Okay, y'all have a good day. See you later. A reminder, if you didn't get your name checked off for attendance, make sure you come talk to me.